My name is Jan Mertens. I'm the Chief Science Officer at ENGIE and also a part-time professor at the University of Gent. So I'd like to talk about the role of CCU in the energy system and how we think that it's more than hiding CO2 for a while. I first want to take a step back and see or talk about how we see this, this CCU story in the overall pathway toward this carbon neutrality that we're after. And I think we see three pathways towards this carbon neutrality, and their order is important. And I think the first one is something that we've been doing for decades. It's all about energy efficiency. So the best energy is the one that you don't use. So there's something that we've started. This is increasing energy efficiency, thinking a lot more circular, but still a lot of the effort will have to come from this, in fact, increasing this energy efficiency. And then the second one is what everybody's talking about, and we as well, and we rightly should. We should try to electrify whatever is possible, and far beyond just our cars. We think we should try to electrify whatever is possible. Sorry, after that. And then the third one, and this is where CCU and carbon capture utilization and e-fuels or CO2 fuels or however you want to call them will come in play. And this is a nice graph which I took from a paper published in Nature at the end of last year, where they use this idea of marginal abatement cost of CO2. So basically on the y-axis, it shows how much does it cost to avoid the emittance of a ton of CO2. And there you see things like passenger cars, but also a lot of things at home, including possibly home heating and stuff like that. If you can do it with electricity, it's probably the cheapest, the most efficient, and the best way to do it. Also in industry, but you see costs start going up. It starts costing more and more. But in the industry, if you can do it with electricity, it's probably a good idea. And you should try to electrify as much as possible also in the industry. But you can see that for large mobility, aviation, shipping, but also long-term storage of energy or long-distance transport of energy, you will probably not do as electricity. We will not store electricity in batteries for months over seasons. It's clear that we will need these molecules. And of course, these molecules can be bio-based, and you can make them from biomass. I will not discuss that today. Today, we're talking about the electricity-based ones. So here you will use the electricity, convert it to molecules to do these things which we cannot do with electricity. And there are multiple. It's not a small market that is left. So there is a big opportunity there for these e-molecules or CCU or CO2-based molecules. I took this figure from the IPCC because they use exactly the same notion of the marginal cost the marginal abatement cost of a ton of CO2. And where you see blue, you can see this is like solar and wind electricity. It's cheaper to do it with electricity. And where you see here, these are the things that you will have to do with molecules. And of course, it will probably be a little bit more expensive because you will need a lot of this electricity and turn it into molecules. So we can actually do high temperature in the industry, long-term storage of energy, long distance transport of energy, aviation, shipping, all these things we will need these molecules which will be made from electricity for a large part. So in 2021, we for the first time reached 10% of our electricity made from wind and solar. You can see Germany and Denmark, of course, already at the end of the last decade taking the lead. But if you see what's happening after 2010, you see a lot of European countries, of course, moving up forward very, very fastly. But also look things like big countries like China and the USA. Today, more than 10% of their electricity actually comes from wind and solar. And if you add mostly hydropower, you end up with around 38% of our electricity generation in 2021 that is made from renewables. So we will need a lot of it to be used as electricity, but also to be converted into the molecules that we will need to do the things that we cannot do immediately with the electricity. And so if we need these molecules, the first obvious molecule that everybody's talking about, I'm almost there to say, is hydrogen. And I will spare you all the different colors of hydrogen. We will mainly focus on the green hydrogen, which is made from renewable electricity, wind and PV. You split your water, as Deepak already said, into hydrogen and oxygen. And of course, you can use your hydrogen and use it in in the industry wherever you need it. So hydrogen, I would dare to say, is the first obvious molecule, right? To be used immediately. But the challenge with hydrogen is really related to its energy density. And this is what we try to depict in this picture here. So if you want to transport or store a certain amount of energy, don't worry, 10 kilowatt hours, it doesn't matter how much. But if you want to transport or store this amount of energy, You can actually do that in 1 liter of diesel or petrol or kerosene. You only need 1 liter to store this amount of energy. If you want to store it in batteries, as I've said before, you would need enormous amounts of batteries, like 27 times the volume you would need to store the same amount of electricity. Now, if you go to hydrogen, it's better, but not that much better out there to say. So you see that if you compress it to 350 bars, you still need to transport and move and store 13 times the same amount of volume around to transport the same amount of energy as in 1 liter of diesel or petrol. Now, if you compress it to 700 bar, you end up with 7 times. You can even make it liquid. We can make hydrogen liquid. We have to go down to minus 250 degrees. But even then, we still have to transport 4 times the amount of energy. And making hydrogen liquid with the technologies that we have today, we lose about 35 or 40% of the energy in the hydrogen to make it liquid. So that's why we think we will need things like methane, ammonia, methanol, all these kinds of synthetic hydrocarbons to actually make this energy transportable and storable. Of course, if you can use hydrogen, if you have a production close by and you need to store it or move it, probably hydrogen is the second best after electricity. But for a lot of cases, we will need to move energy around or store energy around, and we will need these molecules, which is why we spend a lot of effort on these molecules. And so once we agree that we will still need these molecules, this is what we should stop doing. We should stop taking the natural gas out of the ground. In this case, stop taking methane out of the ground for using it in our infrastructure for electricity and heat, because of course we're emitting CO2, and which is what we want to reduce or stop emitting. But we still need the molecules, so we've got no other choice as to synthesize this, as to manufacture it. And that, of course, we need to do, taking CO2 as a base, as a resource from the air or through biogenic, make it react with water. In many cases, you will first split your water with renewable electricity into hydrogen and oxygen, make it react over a catalyst, or as Deepak said, with bacteria. There's 2 ways to do it, but make react CO2 with water or with hydrogen, turn it into the molecule that we're after, because we agree that we still need it for high temperature heat, for long distance storage, for long transport. And then of course we can use it. And this way we can be completely carbon neutral. If you look in the IPCC, carbon neutral will not be enough to help reach the Paris Agreement. Part of the CO2 will also have to store it away, either in products or in CCS. So this is one of the examples that we at ENGIE are working on, but we've got many more. So this is, I like this one because it takes biogenic CO2, which is CO2 actually from the atmosphere, if you wish, but captured by plants in a biogas installation. We take the CO2, so biogas, it's about 60% methane, 40% CO2. We take the CO2, we make it react. In this case, it's catalytically, chemically over a catalyst with hydrogen that we produce from renewable electricity and water, make it react, turn it into methane, which we can then do the things which we cannot do with electricity, as I said before. This is why we think that CCU is more than hiding CO2 for a while. Because of course, what we're doing today is, let's say we've got 2 industrial processes where you take 2 CO2s in the form of, let's say it's methane, out of the ground, you're using your industrial process, and of course you emit 2 times the CO2. Now, a lot of people are saying, but with the CCU, you still emit your CO2, right? Because you take it, you use it, and it's still emitted. Well, it's true. But at least if you do it with, even in the case if you do it with fossil CO2, you capture it, and it's still emitted. You make it react first with hydrogen, you turn into methane, and it's still emitted. So this is true. It is just a delay in the emission of this CO2. But what you have done at the same time is you have prevented taking another one out of the ground. So theoretically, already using fossil CO2, you can save potentially up to 50% of the CO2 emissions, even if you use CO2 from fossil based. Of course, it's not our ambitions. Our ambitions in the long term should be this, where you're completely carbon neutral, where you take your CO2 biogenically or from direct air capture, make it react with your renewable hydrogen made from electricity, which allows you, of course, to be completely carbon neutral. So this is the story on CCU and how we think that we will need CO2 as a resource, and how we will need these fuels. But I wanted to take the opportunity to highlight 2, I would like to say, allies of all these technologies that I've talked about. And we are rightly obsessed with CO2, but I think we are not yet obsessed enough with 2 other things that go along with these technologies. And one of them is this issue of critical materials. If you look at the IEA, this was published at the end of last year. If you look for a car, for example, where I said we should go electricity to electricity, fully right. Of course, we do not need molecules, I think, for your personal cars. Electricity can do the job much better. But if you look at the electricity car compared to a conventional car, you need about 6 times more of these metals. And the same is true for our wind and our PV. Compared to coal and nuclear and natural gas, we need a lot more of these metals to actually succeed in this energy transition. And it's not only true for PV, it's not only true for wind, but even for the hydrogen technologies, your fuel cells, your electrolyzers, and even in the catalyst that we will need to convert the CO2 into molecules, we will need a lot of these metals. And I think we should have more attention to this. And it is not only about having enough, it's also about the environmental impact. So we're doing good things with respect to CO2, but we should really take care to improve our practices with respect to mining environmentally, but also socially, because there are also a lot of social issues related to these minerals. And the IPCC mentioned it in the report, but like, sorry, I've already given away the second one. The IPCC mentioned it in the report in a box, but it was only mentioned for renewables and batteries. I really think also for hydrogen and CCU, and TNO has recently also published a nice report on it, how they could also be a showstopper, or at least show down our ambitions with respect to hydrogen and CCU, and not only for electricity. I think this requires more of our attention if we really want to succeed in the energy transition. And the second one, and then I'll stop, is water. If you look at the overall, this is from an IRENA report from this year, if you look at the overall water consumption that we will need to meet our hydrogen ambitions, it's actually not that large compared to the agricultural water use and the industrial water use. The trouble is, of course, and as already was mentioned by Deepak, a lot of this hydrogen will be produced in areas where we have a lot of sun, where PV electricity is cheap and abundant, and those usually do not coincide with areas where you have access to lots of clean water. So I think this is a second one, second climate change ally, as I like to call them. It goes along with the CO2, which deserves more of our attention.